Hello! In this video, we are going to prove the following theorem. Let G be a finite group and let H be a subgroup of G. Then the order of H divides the order of G. Now this theorem is sometimes called Lagrange's theorem. Now, to prove it, we are going to be using properties of the sets of this form, of the form AH. Now, what is this set exactly? Well, given that G is a group, H is a subset of G, and A is an element of G, then the set AH is the set of all elements of G of the form A times H, where H is some element of H. So you can imagine taking all of the elements of H and multiplying them on the left by A, and that forms this set. Now in the case where H is a subgroup of G, this set is called a left coset of H in G. So in proving this theorem, we are going to be using a lot of properties about sets of this form. So now, let's get into proving this theorem. To start the proof, we are going to denote the collection of all left cosets of H as follows. So the collection of all left cosets of H, we will call that set G colon H. Now this set is clearly a finite set, right? Because every element of this set is a subset of our group G. So in other words, every element of this set is an element of the power set of G. So since G is finite, it follows that the power set of G is finite. Well, since this set is a subset of the power set of G, we know every subset of a finite set is finite, so this set must be finite. So, because this set is finite, let's denote the number of elements in this set by n. So because the number of left cosets of H is n, this means we could distinctly list all left cosets of H. Right, so let's say we distinctly list all of them as L1, L2, all the way up to Ln. So we can distinctly list all n left cosets of H. Say we do it like this. So another way of putting that is there exists a bijection from the set of the integers between 1 and n and the left cosets of H. So then what do you think happens if we take the union of all of the left cosets of H? That should just result in the entire group G, right? That's our claim. So to prove that, we're going to prove that the union is a subset of G, and G is a subset of the union. So let's first prove the union is a subset of G. We'll do that by giving ourselves an arbitrary element x in the union. Well then, this means that there exists an integer I between 1 and n such that x is an element of Li. Now Li is one of the elements of this set, but every element of this set is a subset of G. So Li is a subset of G. So every element of Li must be an element of G, so since x is an element of Li, x must be an element of G. And so that's it. We have shown if x is any element of the union, then x must be an element of G. Therefore, the union is a subset of G. But now let's show that G is a subset of the union. To do that, let's give ourselves an arbitrary element of G. I'll call it y. Well then, a property about cosets tells us that y must be an element of the coset YH. Right, this is a property about cosets that we have proven, which is the following. Given that G is a group, H is a subgroup of G, and A is any element of G, then A must be an element of the coset AH. So applying this result in our proof, Y must be an element of YH. But we know that YH is an element of this set. So since this function is surjective, that means there must exist some integer between 1 and n. I'll call it k, such that YH is equal to LK. So we see that Y is an element of LK, and therefore Y is an element of one of the sets in the union. Therefore, Y must be an element of the union itself. So this shows if Y is any element of G, then Y must be an element of the union, and therefore G is a subset of the union. So the union is a subset of G, and G is a subset of the union, therefore these two guys are equal. So this proves our claim, and it's going to be useful. Now next, remember, the collection of all left cosets of H is a finite set. But not only that, every left coset of H is a finite set itself. Because every left coset of H is a subset of G, which is finite. Right? So every element in here is finite, and so that means all of the sets L1 through Ln are finite sets. But the claim is that this collection of sets is pairwise disjoint. Because if we can show that, it would follow that the union of all of these sets is finite. And the number of elements in the union of all of these sets must be equal to the number of elements in L1 plus the number of elements in L2, and so on, plus the number of elements in Ln. But since we know the union itself is equal to G, that gives us an idea of the number of elements in G. And we're going to try to express the number of elements in G as a multiple of the number of elements in H. So with that in mind, let's show that this collection of sets is pairwise disjoint. To do that, let's give ourselves two arbitrary integers, I and j, between 1 and n. And suppose I is not equal to j. From here, we want to show that Li and Lj are disjoint. Now, since this function is injective, it follows that Li is not equal to Lj. But we know that Li and Lj are elements of this set, so we can say Li is equal to AH and Lj is equal to BH, where A and B are some elements of G. So since Li is not equal to Lj, that means we have AH not equal to BH. But from here, we're going to use another property about cosets, which is the following. Given G is a group, H is a subgroup of G, and A and B are elements of G, then the cosets AH and BH are distinct if and only if they are disjoint. So applying this in our proof, since AH and BH are distinct, they must be disjoint. Or in other words, we just substitute AH for Li, substitute BH for Lj, we have Li and Lj are disjoint. And so we're done. We have shown that this list of sets is pairwise disjoint. So now we can conclude that the union of all of these sets is a finite set, and that the number of elements in the union is equal to the number of elements in L1 plus the number of elements in L2, all the way up to the number of elements in Ln. But remember, the union itself is equal to G, so this is the same thing as the number of elements in G. But what do you think the number of elements in any left coset is going to be equal to? The number of elements in any left coset of H should be equal to the number of elements in H itself, right? Now to show that, we're going to be using the following property. Given that G is a group, H is a subset of G, and A and B are elements of G, then the cardinalities of AH and BH are the same. So let's use this to show that every left coset here, so given any integer I between 1 and n, we can show that the number of elements in Li is equal to the number of elements in H. So how do we show that? Well, let's consider an arbitrary integer I between 1 and n. Well then, Li is an element of this set by definition of our function. So Li, element of this set, it's equal to AH for some element A and G. But now we apply this result, right? In this case, G is a group, H is a subset of G. We're going to take A to be the A we have here. We're going to take B to be the identity element of our group, so E. So in that case, we can conclude that the cardinality of AH is equal to the cardinality of EH. So we have cardinality of AH equal to the cardinality of EH. But what is EH? EH is just H itself, right? Remember, EH is just taking all the elements of H, multiplying them on the left by the identity element. That doesn't change the set H itself. So EH is actually equal to H itself. So this shows that the number of elements in AH is equal to the number of elements in H, but remember, AH is equal to Li, so we're really saying the number of elements in Li is equal to the number of elements in H. So given any integer I between 1 and n, the number of elements in Li is really just the same thing as the number of elements in H. So in that case, every term of this sum is precisely the number of elements in H. So we're adding the number of elements in H n times. So this is the same thing as n times the number of elements in H, but n is the same thing as the number of elements in G colon H. So really this is the number of elements in G colon H times the number of elements in H. Right? So we see, right, since these are all integers, the order of H divides the order of G. And so that's it. This completes the proof. And so we see more specifically how exactly the order of H divides the order of G, right? What we've more specifically proven here is, given G is a finite group, given H is a subgroup of G, if we define G colon H to be this set, then it will follow that the order of G is equal to the number of elements in G colon H times the order of H. Right, so this equality will be true. Now, this number is sometimes called the index of H and G. Right, it's the number of left cosets of H and G. And so yeah, that's pretty much it for this video.